Okay, so now we are looking at lesson 4, geometric distribution. So here are some things to consider, some examples to get your mind thinking about what a geometric distribution looks like. So in some board games, you cannot move forward until you roll a specific number, which could take several tries. Key words here, several tries. Manufacturers of products such as switches, relays, and hard drives need to know how many operations their product can perform before failing. So here, how many operations their product can perform before failing. Let's use a highlighter here. And in some sports competitions, the winner is the player who scores the most points before missing a shot. In such situations, the critical quantity is the waiting time or the waiting period. So if you look above, all these have in common that something has to happen before a desired outcome or failure or whatever that checkpoint is, the number of trials before a specific outcome occurs. This type of problem is modeled with geometric. So with all our other lessons, we were looking at the probability, we were looking at different possibilities like binomial distributions, Bernoulli trials. In this case, we're not concerned with how many successes we have. We're concerned with how long we have to wait to achieve that success. So do I have to roll a die 3 times before the 4th time getting the desired outcome? How many times do I have to wait before I can get this desired outcome? So that's in essence what a geometric distribution is. So given a situation of Bernoulli trials, again, just reminded, Bernoulli trials, identical, independent success-failure outcomes. So it's success or failure, one or the other. The number of trials prior to the first success is called a waiting period before a success. And that's what we're looking at with geometric distributions. So let x be the random variable equal to the number of trials before a success. And the probability distribution of x is given by P, the probability distribution of x is equal to Q to the power of x times P. So P is the probability of success on each trial, and Q would be 1 minus P, the probability of failure. And a reminder, we're looking at success, failure. So basically, if 60% was my success, then the failure rate would be 40%. Okay, it's 1 minus the 60. So x can equal 0, 1, 2. The expected value, so again, the mean here, is the random variable that is geometrically distributed. So that's Q over P. So let's look at one more thing I want to mention here. Technically, so x could be 0 weights, and I can get the success or my desired outcome on the first try. I can get it on the second try, and so on. You can technically go up to infinity here because, sadly, you may never reach that outcome that you want. And so all your trials can continue, and you don't reach the outcome you want. Or in a positive outlook, if you are looking to see how many trials before your product, say, has a failure, it may never reach a failure. So you have a great product there. So there are times where you could potentially never reach that, quote, success. And by success, that could be meaning my product will never fail, or that can also mean getting a desired outcome like, I don't know, rolling a 6 on a die. So when will this first success happen? So let's look at a repeated roll of a pair of dice. So again, we are familiar with this chart now. 1, 2, 3, 4, 5, 6. It's a fair die. And we're looking at what is the probability that the first roll of doubles occurs on the third roll. Okay, so our success is a double occurring. And I'm not going to fill out this whole chart, but you can see here 1, 1, 2, 2, 3, 3. So we're going to look at how many trials are going to occur before getting a double. So this is our random variable x. Let x represent the number of trials before getting doubles. So x can be equal to 0, 1, 2, and so on. I don't know how many trials it's going to happen. What is the probability that the first roll of doubles occurs on the third roll? So I basically am looking for first, second, third. I want it to occur here. This is the first roll, doesn't happen. Second, doesn't happen. And the roll of doubles happens on the third. So it's pretty specific. So we want success to happen on the third roll. We're looking for our wait time. So our wait time here is basically 2. So let's find the probability of that now happening. I guess I'll do this in different colors so you can distinguish it. The probability of success out of 36 options, rolling a double can happen 1, 2, 3, 4, 5, 6 times. So 6 out of 36, meaning the failure would be 1 minus 6 over 36. So Q would be 30 over 36. So using our formula, we have the probability of failure here, 30 over 36, to the power of x. And in this case, x is your wait time, and in this case, your x is 2. I'll write that out here. X is equal to 2 because we have to wait 2 times to reach success. And our success rate would be 6 out of 36. And so you take your calculator and you can type this all in. So 30 over 36 to the power of 2 times 6 over 36. That gives us 25 over 216. This is probability, so I can divide that out. So I have a 0.1157, which is approximately 12% chance of getting the first doubles on the third try. And now we're looking for what is the expected wait time, the number of rolls before you roll doubles. So the expected wait time, so if I was just rolling the 2 dice, I'm trying to figure out how many rolls will it take before I get it. Remember, this is not probability. So I take my failure over P. You're dividing 2 fractions, so I'm going to write it out this way because that makes it easier to visualize it. And now we know to divide. Switch to multiplication, reciprocal of the second, and you're left with 30 over 6, which is equal to 5. So therefore, we'd expect to have a waiting time of 5 before rolling doubles. Okay, so that would be doubles there. So this is what geometric distributions look like. So let's look at example 2. Example 2, what is the probability of rolling a sum of 7 in fewer than 3 rolls of a pair of dice? So I need a sum of 7, fewer than 3 rolls, pair of dice. On the side here, I'm not going to draw out this whole chart, and hopefully you still have access to the charts that I originally posted with these summations. I'm looking for a sum of 7, so I'm not going to fill in this whole chart here. I basically want to fill in where I have 7s, because that's really what I care about here. You should have access to the chart. So 1, 2, 3, 4, 5, 6. There are 6 possibilities out of 36 to get my P. Which gives me Q of 30 over 36. Let's just fill this out here. Let X represent the number of trials before getting the first sum of 7. So let's look at this. So if I have fewer than 3 rolls, so I have 1, 2, 3. So I could get a sum of 7. This is the first, second, third. I can get it on the first one, which would mean I have a weight of 0. I could get it on the second one, which means I would have a weight of 1. And it has to be fewer than 3. So I'm not looking at the third one, so it has to be fewer than 3. So that would not count there. So I'm looking for, let's change this color here. I'm looking for a P where my random variable X is less than 3, because it has to be fewer than 3 throws. So I'm looking at a probability of 0 weights, I get it on the first throw, or a probability of a weight of 1. So I get it on my second roll. So now we can use our formula. We're going to do it twice here. I have 30 over 36 to the power of 0, because my X is 0, times 6 over 36, plus, same thing, 30 over 36 to the power of 1. So you can use your calculator here, and we are looking at 30 over 36 to the power of 0, which is 1, times 6 over 36. That gives me 0.167, plus 30 over 36 times 6 over 36, 0.139. This is a probability. Add them up. So therefore, you have about 30.6% chance of getting a sum of 7 in fewer than 3 rolls. And the last one here, we have Jason, who has a success rate of 68% for scoring on free throws in basketball. What is the expected wait time before he misses the basket on the free throw? So this is a bit of backward thinking here. Success rate of 68%. What is the expected wait time before he misses a basket? So I'm trying to figure out, when is he going to miss this basket? So my P, let's go backwards here. My Q is him getting the basket, 0.68. My P would be 1 minus 0.68. Okay, so a reminder, your P is the probability of success. I'm trying, the success in this case, I might write this on the side here, the success is missing a free throw. Okay, so the success is missing a free throw. So the probability of success would be missing. So it's 1 minus 0.68. So it's 0.32. Okay, so in this case, we're trying to figure out how many times is he going to get these baskets in, which is at a rate of 68%, before he misses a shot. So let's let X represent the wait time before missing. So he's getting all these shots in, and then finally he misses a shot, and that's our criteria we are looking for. We're looking for expected, so expected wait time is equal to Q over P. This is not probability, so we can take our Q That's him actually getting a basket divided by not getting a basket. And that gives us 2.125. So basically, we would say we can't have a 2.125. It's discrete. We expect him to miss his first shot on the third basket. So we'd expect Jason to miss his first shot after 2 baskets. So on his third. So by the time he goes for his third shot, he misses. Okay, based on his 68% scoring of free throws. So that is what geometric distribution looks like.